So hello everyone, my name is Operlejn, and I would like to introduce you to the topic of neural network training with noisy labels. So what to do when annotators fail. So the motivation for creating this presentation and sharing it with you is my consideration of starting a PhD. I'm in a stage of looking for some research gap to develop in particular direction. So the topic of label noise just seemed interesting to me. I made some research. I am by no means any authority on the topic, but well, I want to share the knowledge with you that I gathered throughout, this time of the research. All right, so let's start with the agenda. First of all, I would like to specify the motivation and describe why this is important issue and in data science field. Then I will tell you something about the problem definition and will tell you what kind of noise we can expect in our labels. Then I will briefly describe the basic but effective methods of dealing with noise labels. And well, I will outline some conclusions and obviously provide you with some references, some research papers and websites if you would like to know more about the topic. So as you can see, I mentioned that I will present only the basic methods today. It's due to the amount of material that we decided to divide the deep talk into two parts. So in the second part, I will talk about some advanced methods with SOTA results. So it will pace over the coming years. So if you will be interested, then I can invite you to join already. So the introduction and motivation. Basically, anyone familiar with computer vision and with computer vision in research knows that despite the massive volume of data, usually the same data sets are used over and over again in publications, in research papers. And it obviously makes sense because we want to compare our results with others. So the most popular data sets have noisy labels in rather small amounts. So for example, here in ImageNet, we got 6%. Also in CIFAR 100, 6% of labels which are incorrect. So they actually, the image on the picture represent something else than the label. So for example, here we got some errors from labelerrors.com. This is website which gathers all the errors in the most popular computer vision datasets. So as you can see, apparently we got an ear here or a nipple, apparently. So also the quick draw, which is also popular dataset, have like 10% of noise. And what is interesting, even MNIST isn't flawless. So I assumed that it is easy to annotate the numbers, the digits, but apparently it is not so easy because we got 15 images which are incorrectly labeled. Okay, so we know that we can usually ignore this noise because we got some regularization methods like dropout and early stopping to prevent overfitting. So we can focus on other awesome stuff instead. So for example, improving architecture just a little bit, or maybe apply some nice tricks, all the things we love in the scientific world. So we will achieve some better result by 0.001% than state of the art. Then we can publish a paper and everyone is happy. So this is the almost ideal world of science. We know that it isn't the case in the real world scenarios. Well, the data we need for our purpose in the real world might be labeled partially or not labeled at all. So, well, we want to gather the labels, or maybe do it by ourselves. We know that there are some tools of labeling, for example, Labelbox, but well, they are fine, but it is time-consuming process to annotate. Well, even for the classification problem, when we need to just put an like particular class for each image, not mentioning the segmentation problem, for example, when we need to draw this box, and well, it's much more complex and time-consuming. So maybe let's delegate it, right? We could do that, but it is expensive because we got some data labeling companies which can be beyond our budget. So there are some cheaper sources, right? So for example, Amazon Mechanical Turk, which is a crowdsourcing source. I mean, the website, which as you see, can make money in your spare time by, for example, labeling the data as a regular human being and not an expert from labeling. Well, it can be inaccurate, as you can imagine. So, for example, maybe the people don't have experience in labeling, maybe they are just lazy, or maybe the labels aren't double checked. So this is another problem. Another problem is that it can be difficult to annotate the data because, for example, here we got low quality of data. I can imagine this is a parrot, but I have no idea what exactly is that. And for other people, it can also be a bit problematic. Also, the different interpretations of the labels can be a problem. So, for example, well, this gentleman can be obviously annotated as human being, but we also got a phone, a watch, or maybe a plant. So, well, we cannot know, or maybe we can know what is our problem, but maybe another outsourced annotator will have the problem of labeling it. And also, the lack of expertise can be a problem. So, as you know, well, it would be difficult to annotate, for example, liver tumors in computer tomography scans. So even radiologists could have some problems and could have different interpretations, which, well, is coming back to this point of the interpretation problem. So these points are actually main sources of noisy labels. And as I showed you before in the, well, this well-known data sets, this is not a big problem because this percentage isn't big. But in the real world, it can be much, much bigger. But why would we care if the deep neural network can be robust to it? Well, there's an interesting paper which was published in 2017. This name is Understanding Deep Learning Requires Rethinking Generalization. And as you can see here on the graph on the left, we got some experiments which they conducted. So first of all, they had just a normal regular training with true labels, which converged pretty quickly. So the loss approached zero very quickly. And then we got some shuffled pixels or random pixels introduced in these pictures, so in the data features. And still the neural network could feed the data and, as you see, converged. The real interesting case for our scenario is that even introducing completely random labels, even this model could converge. Obviously, it took much more time than for the previous examples, but still, it means that even if this training potentially doesn't make sense because we got totally random labels, then our neural network will remember, we will memorize these labels, and then it will overfit at some point of time. So obviously, the time to overfit will increase if we will introduce more corruption to the labels, but also the test error will increase till 0.9 if we got like 100% of labels wrong. All right, so, well, this is why we need it, just basically to prevent it from overfitting. So we don't want to remember these noisy labels as the true ones. So the fundamentals of noisy labels. Basically, we all know what noisy labels are, but we got a taxonomy of, so the categorization of the label noise. First of all, we got instance-independent label noise. So it's the most common approach for modeling label noise, and the noise is conditionally independent of data features. I will explain what does it mean in a little bit. I would like to present you the noise transition matrix, which represents the noise as a form of the matrix. So here we got a symmetric one. So basically, the noise transition matrix is conditioned by the probability of the true label I being flipped into a corrupted label J. So, for example, here we got a true label A. So let's imagine it is an apple. We have 100 apples in the dataset, but only 85 of them are actually annotated as apples. So here, as you can see, we got 85% of well labeled data. The remaining apples have other labels, such as in this case orange, banana, or pineapple. So as you can see, we got some different labels here, different classes here, and we got 5% of the true class, true label A being misinterpreted or being represented in the dataset, the noisy dataset, as for example class C. So as you can see, it's summed to 100 because it's like a probability. And then we got the thing for all classes. So as you can see, we have equal probability here because it's a symmetric noise, so symmetric noise transition matrix. So it means that the true label is flipped into another labels with equal probability. Then we got more real scenario when there is an asymmetric noise transition matrix, which means that some classes are more probable to be flipped into another and some not. So for example, here we can see once again we got 85% of label A to be actually annotated as A in the dataset, and 15% that it will be annotated as B, as an example. Then we got a true label C, which has 99% of being labeled as C. So this is probably a clean example. So we cannot misinterpret it as another class. So we got only 1% that it will be flipped into the class A in the dataset. This is more common noise because, for example, we can imagine that it can be difficult to distinguish 1 from 7 in the MNIST dataset. So it is far easier to distinguish the ones from 8s than, for example, ones from 7s, right? Because they are more similar. So we can imagine that. Or here, for example, the real world scenario where people has some problems in the ImageNet distinguishing the cassette from the cassette player. So there is a cassette inside, but still it's like two different classes and people misinterpreted it and labeled it differently. So this is the instance independent label noise. And here we got instance dependent label noise. So it's more realistic noise modeling. So noise is dependent on both the data features and class labels. So as you remember here, we had only the class dependency. So we didn't even look at the features of the data. Here we are looking at the features. So I prepared for you an example with dogs, because who doesn't like examples with dogs? So we can assume that the example model usually has no problem distinguishing the dog class from other classes. So you can see here that this doggo, there's no problem from labeling it. But for example, in some other cases, we know that case. So the difference between muffin and the dog. So we know that, for example, in this kind of breed of the dog, there is a problem to interpret it. So it can be interpreted, it can be labeled as muffin. For example, this cutie can be labeled as snowball for some reason. Maybe somebody is a little bit blind. So as you can see, it is not like all dogs have equal probability to being mislabeled as muffin. It's like this particular breed of dog has it. So that's why it is dependent on the data features. All right, so these are the types of noise we are dealing with. This one is much more realistic. And now I would like to, my goal is to briefly describe a few of these most important methods and architectures as a high-level overview. So without going into detail, if someone is interested, I left some references at the end of the presentation. Okay, so here for starters, let's look at the different branches of this field. So this great illustrations comes from this survey, which is very great. It was published in 2022, and it basically gathers all the information about the state-of-the-art models and also the older ones. Today, we will focus on this branch, so robust loss function and loss adjustment. We got also like sample selection, so filtering the samples from the noisy samples from the dataset. We got some regularization methods which are pretty great to make the network robust. We got also the ready-made architectures to deal with noisy labels. yeah, so as I said, we will focus now on this particular method, and on part 2, I will present you much more interesting cases with sort of results. First of all, well, a small reminder for next slides, because for classification, we are usually using cross-entropy, and it will be presented in different fonts today. So just remember that we have a cross-entropy problem here. So we got loss correction. And as you can see, it is based on this transition matrix. So it's just adjusting the loss by multiplying the output of a deep neural network by the estimated transition matrix. So we know we got this transition matrix. So we know what is the probability that class A will be mislabeled as class B, right? So basically, we can multiply it in the loss function. So as you can see here, the T element is the transition matrix. We can just introduce it into the equation, and then we will have the loss fixed for us. Well, as you can see, there is a backward correction and forward correction. The only difference is that we are introducing this matrix in another place on the equation. So these were 2 experiments in one paper, which was originally published in 2017. So this is the great but basic method of reducing the impact of noisy labels for our dataset. So the problem with this method is that we need estimated transition matrix. So as we know, well, it's difficult to assess what noise do we have in the dataset, because we are not counting the examples. It would be probably very useless to count the example by example and then creating it by our own. So actually, the authors of this paper proposed one method, which is basically described on this slide. So we want to take the perfect example from each class as an input data, and then taking the model output. So we are looking for, not trained, so it's not a training example. We are gathering some other perfect examples. So we need one perfect example per class. So for example, here we got an apple of, it's a beautiful apple, so we know it's a perfect example in our case, and it cannot be misinterpreted, right? So we are basically giving it as an input for our pre-trained model. The model was trained on noisy data. That's why if we know that this is a perfect example, so the softmax should be, approaching, the class A should be approaching 99% or even more, then we know that, for example, here, then the noise, the mistake of the softmax should be due to the pure noise. So we can actually take this softmax output and use it as our column in transition matrix. So here we are having an apple, then we are having orange, then we are having banana and pineapple, and at the end we will have the matrix. Obviously, this method is not perfect because it's not easy to estimate it. I mean, it will improve the results, but still it's not a perfect scenario. So the whole algorithm looks like that. So we got the T's of the transition matrix, which is unknown, and we are training the network with the noisy labels, as I described it to you. Then we are gathering some different samples, which were previously not used to train the model. So we are looking for these perfect samples, and then we are estimating the transition matrix, and of course, retraining the model once again, this time with this loss correction. This is, another method that works on similar principle, but this time the estimation of transition matrix is done automatically, which means we are adding a new layer, and it's just trained, and these trainable weights are they will finally form a transition matrix for us. Here we got label refurbishment. The method is called bootstrapping, and it's probably the oldest method of dealing with noisy labels. So basically, it's a combination of ground truth label with predicted label. So we are mixing both prediction and the ground truth label in some proportion, but dictated by the beta hyperparameter. So intuitively, as the learner improves over time, its predictions can be trusted more, right? So we are punishing less for the original prediction, so the prediction different than our model, than our ground truth. Okay, so basically, we got two methods of bootstrapping, so soft bootstrapping and hard bootstrapping. I want to, I want you to have the intuition behind that. So we got this equation. Once again, it's like cross entropy loss. So we got original true label apple, which we actually knows that is noisy, because we see that in the photo there is actually orange, not apple. And model prediction is also orange because the model is trained pretty well. I mean, some epochs passed, and it is sure that it should be orange. So in this case, the label is corrupted, so the normal cross entropy loss will be higher. So it shouldn't be. So maybe let's trust the model more and think that, well, it can be actually orange in some percentage, right? So that's why we are introducing beta. So let's say beta is like 0.8. So we are having 0.8 of true label, possibly noisy, and we are having 0.2 of this predicted label, right? The difference between soft bootstrapping and hard bootstrapping is that here we are multiplying this element by softmax value. And this time, this ZK is just an argmax of predictions. So basically, we're taking the most confident prediction and making it 1, and other are 0. So we got one hot encoded vector. So here it is showed in the code. So we got soft bootstrapping loss. And as you can see here, we got first term and second term. Basically, this is an unofficial implementation of this paper, so, and further modified by me for the readability purposes. So if you're interested, there is a GitHub page with the whole code. I will also link you some of my experiments, probably somewhere in the description. Right, so we got two terms, first term and second term, which is basically, as you can see here, we are multiplying this logarithm by two terms, and that's why we are having these two terms. So we got minus beta times t, so the true prediction, and the logarithmic equation. So this is the first term, and this is the second term right here. So it's just applied formula to the code, and then we are taking a mean for all samples, and that's it. And the only difference between soft and hard is that here we are introducing this one hot vector instead of softmax. So this is the only difference. And while in the original paper we had it fixed, so this beta parameter was fixed, then maybe I'll describe it later, because an example to show you is yet before us. So here we got input. So input for our loss function. So these are the predictions of the model. So the model predicted that this is probably the most, this is the class prediction is probably 1 and 1. So as you can see here, the biggest input values are in the first index, right? In the not 0 but first, because we are iterating from 0. And actually the model will say that no, this is the true labels will be 0 and 2. So well, our model predictions are wrong from the definition of the target variables. But we know that they are right. Let's imagine that. So we got soft bootstrapping loss with beta equals 0.9. We should rather trust the annotations, not the model, because 0.9 is like, approaching 100%. Then we got cross entropy loss, which is like our baseline loss. And here we got outputs of the loss. So as you can see here, we got 3.26 for just normal cross entropy loss. And then we got 2.97 and 2.94 for our bootstrapping losses. So as you can see, the loss is reduced because we trust the model a little bit. And then if we will change the beta to be 0.4, so we are trusting more the predictions, then as you can see, the loss will be reduced in a significant amount. So once again, we got this example, and in this time, the loss is reduced significantly, right? So that's the bootstrapping loss. Yeah, and in the original paper, the authors proposed a fixed beta parameter. So it was 0.8 for hard bootstrapping and 0.95 for soft bootstrapping. And actually, well, it would converge, but it will be delayed. So the new approach is to use the dynamic bootstrapping. And I will present it to you in this slide. So here we can see the normal training with clean and noisy labels. So at the beginning of the training, we can see that it is easy to distinguish the clean labels from the noisy ones, because it is the loss will decrease in like easily for the clean labels because the model is learning, and it will be a bit robust at the beginning for the noisy labels. So it will have higher loss for the noisy ones, the noisy examples. And then at some point of time, it will converge because it will memorize it. So the model will overfit. So in the example of dynamic bootstrapping, as you can see, the noise, the loss can be easily separable. So it means that we can separate the noisy examples from these clean examples and then learn with them, right? So the dynamic bootstrapping is basically the beta parameter which will change over time. And how it will change, we will describe it in the next part, because it's, well, more complex than how to estimate the beta is more complex. All right, so the last method for today, once again, we are playing with loss, is, well, it's combining some loss variables, I mean loss functions, into one normalized. But let's imagine, let's just focus on cross entropy, which is completely not robust to noisy labels because of its characteristics. As you can see here, if we got a clear labels, so no noise at all, the cross entropy for the test is pretty good. I mean, it's regular, better than a mean absolute error, obviously. Then if we will introduce some noise, so for example here 40% of noise, it will overfit. So it will increase and then decrease slightly. Now we have 80% of noise, and it will overfit once again. For mean absolute error, it is robust to label loss. So as you can see here, it is well, better, right? So than cross entropy, but it has underfitting problem. So there is a solution to address both problems, and doctors hate it. So it's a normalization of loss, which makes it robust. So you can see here the cross entropy and focal loss will overfit, and then normalized, so scaled from 0 to 1, it will do just fine. It is not always the case, because, for example, for normalized mean absolute error, it will achieve worse results. And then we can combine two different losses, which will improve the model performance. So we are dividing we got two categories of losses. So an active loss that maximizes the probability of belonging to the given class. So for example, the cross entropy or focal loss. So as I said, it is a bit not robust, but still we can use it. Because it achieves better results with low noise. And then we got some passive losses that minimizes the probability of belonging to another class. So we get mean absolute error, for example. Then we are connecting them in one loss. And as you can see here, the cross entropy in the black overfits. The mean absolute error here, it's achieving good results. But for example, for Cypher 100, it is underfits. And for the combination of both passive active losses, we got very, very nice results. And as you can see, the implementation once again is very easy. So we are just combining two noises by alpha and beta, so some proportions. And here, my experiment, it actually works. So it doesn't overfit the data. So summary. Even small tricks like changing the loss or simple selection of clean data can strengthen the robustness of the network. So in just a few lines of code, we can know that we have noisy labels in our data, so it can help with our noisy labels. But there is still much to explore. So in the next part of the tutorial, I will introduce a niche method of regularization, with great results. It can also be used for non-noisy labels, and it's not popular yet, but I believe in a few years it will be much more popular because it works great. Then we'll have semi-supervised classification model, and last but not least, we got advanced methods of training with noisy labels with SOTA results. So actually, I only introduced you the forward correction right now from these SOTA methods, and then we will have co-teaching, divide, mix, and generally speaking, much better methods from recent years. These are the references. This is the survey I was talking about. Also, we got some GitHub pages with. This is the awesome one because it has all implementations of all methods of training with noisy labels. We got also the bootstrapping loss and a great tutorial from this survey that introduces the active passive loss, and I also used their code to my purposes. And that will be it. Thank you for your attention.